You know how a single piece of new information can just completely change the odds of something? Like a cloudy sky makes you rethink those picnic plans, right? Or a sudden traffic report makes you take a totally different route home. Well, there's actually a whole branch of math behind that feeling. It's called conditional probability, and we're going to dive into how knowing just one thing can fundamentally change the chances of another.
So, let's kick things off with a really simple question. We all know, just from experience, that the chance of a car accident on the highway isn't some fixed number. But what if I tell you it's snowing? Suddenly, the probability of an accident goes way up, doesn't it? That big shift, all based on the condition of snow, well, that's the heart of what we're talking about today.
Okay, so here's the game plan for this explainer. First, we're going to give that what if feeling a proper name. Then we'll get into how to actually calculate with these new conditions. After that, we'll tackle a super important question. Does knowing something new always make a difference? And to wrap it all up, we'll see how this whole idea helps us spot hidden connections in the world.
All right, let's jump right in. For this first part, we're going to move past just our gut feelings and start using some real hard data. It's time to see how new knowledge actually changes the odds and, finally give that what if feeling an official name.
Okay, so let's look at some actual data. What you're seeing here is a table from a survey of 200 students, and they were asked about two, well, kind of random skills. Can you roll your tongue? And can you raise just one eyebrow? It might look like a simple little grid, but trust me, hidden inside these numbers is the absolute key to understanding conditional probability. So here's our first real question. I want you to forget about all 200 students for just a second. Instead, imagine we pick one student completely at random, and I tell you, hey, this person can raise one eyebrow. Now, with just that one little piece of info, what do you think the chances are that they can also roll their tongue? And this is the critical step, because we know for a fact that our student can raise an eyebrow. Everyone else, those 138 students in the bottom row, they're suddenly irrelevant. We can literally just ignore them. Our entire world of possibilities has just shrunk from 200 students all the way down to just these 62 people in that top row. Okay, so now that we're only looking at our new universe of 62 people, the table tells us that 42 of them can also roll their tongue. The math is simple from here. It's just 42 divided by 62, which is about 67.7%. And just think about that for a second. Knowing that one little fact about their eyebrow dramatically changed the odds. So what we just did, it has a name, of course. It's called conditional probability. And all it means is the probability of one thing happening, we'll call it event A, given that another thing, event B, is already a done deal. The notation for it looks like this: P, then A, a vertical line, then B. And we just read that out loud as the probability of A given B. Okay, so working with a table like that is great. It makes things really clear. But what happens when you don't have a neat little table? We need a tool that works every time. So in this next part, we're going to take that gut feeling we just worked through and turn it into a really powerful all-purpose formula. And there it is. The formula says the probability of B happening given A has already happened is just the probability of A and B happening together divided by the probability of A happening in the first place. I know it looks a little mathy, but it's really just a formal way of saying what we already did. Figure out the chance of what you want happening inside that new, smaller world of what you already know. All right, let's put this formula to the test with a completely new scenario. Let's say we've got survey data about what newspapers people read in a big apartment building. So we know who reads USA Today, who reads the New York Times, and who reads both. Here's the question. If you bump into someone and find out they read USA Today, what's the probability they also read the Times? Okay, let's just plug our numbers into that formula. The chance of someone reading both papers, that's our A and B, is 3%. The chance of someone reading USA Today at all, that's our A, is 20%. So we just follow the formula. We divide the both probability by our given probability. So 0.03 divided by 0.20, and that gives us 0.15, or 15%. Boom! Knowing they read USA Today means there's a 15% chance they also read the Times. Okay, so up to this point, every time we've gotten a new piece of information, it has changed the final probability. But does it have to? And that question leads us to our next huge idea, independence. Because sometimes knowing about one thing changes absolutely nothing about the odds of another. This chart here lays it out perfectly. On one side, you have independent events. That's where knowing one thing happened does not change the probability of the other. The classic example is a coin toss, right? If you get heads, the chance of getting heads on the very next flip is still 50-50. The coin doesn't remember. But on the other side, you have dependent events. That's like our tongue rolling and eyebrow raising example, where knowing one thing absolutely did change the odds of the other.
So how can we actually test for this stuff with numbers? Well, it's actually pretty simple. You just compare the probabilities. Let's go back to our students. The chance of being able to raise an eyebrow, given you can roll your tongue, is about 28.2%. But the chance of raising an eyebrow, given you cannot roll your tongue, is way higher, about 39.2%. And since those two numbers are not equal, we've proven it. The events are dependent.
And all of this leads us to our final and maybe the most important section. Why do we care so much about this whole independence thing? Well, here's why. Because when two things are not independent, when they're dependent, that's a giant flashing sign that there's a connection, an association between them. And finding those associations, that's a huge part of how we make sense of the world.
Okay, let's look at one last example to really drive this home. Here we have a table from a survey of 100 teachers, and it looks at two things, whether they teach math and whether they're left-handed or right-handed. Now, at first glance, it just looks like a bunch of numbers. But let's ask our big question. Is teaching math independent from being left-handed?
All right, here's the test. First, what's the overall probability of any random teacher in this whole group being left-handed? Well, it's 10 out of 100, which is exactly 10%. Okay, but now let's narrow our world down and look only at the math teachers. For them, the probability of being left-handed is 7 out of 46, which is more than 15%. And there's our answer. Since 15.2% is clearly not equal to 10%, these events are not independent. And this is so cool because it's more than just numbers on a page. It's actual statistical evidence that there's some kind of association going on here. For this group of teachers, knowing their subject genuinely gives you a clue about which hand they write with.
And look, if the numbers weren't convincing enough, this bar chart makes the association visually undeniable. You can just see the difference. That blue slice representing left-handers is so much bigger for the math teachers than it is for the other teachers. The math proved the connection, but this visual makes it absolutely impossible to miss.
So, let's end with this idea. Conditional probability and independence, they aren't just things you learn for a math test. They're actually tools for being curious. They give us a powerful way to ask, what if? And to start uncovering all the hidden connections that are happening around us all the time. So the real question is, what hidden relationships in your world could you uncover just by asking, what if?